Recording begins. So today we'll follow on from what we covered on Tuesday. And if you know anyone who got confused with assembly, I think I definitely encourage your friends, if they're not here, please tell them to join because it's gonna get more confusing, and I want to make sure if there's any confusion, we will address it in the lecture, right? That's one main purpose of the lecture, even though that this is recorded. It's different when you can interactively ask questions, all right? But now we continue on and look at how do we write loops, right? So on Tuesday, we talk about the jump instruction where you can say, hey, I can jump to the destination. What should go into the destination here? Can someone tell me what go into the destination? What would go in there? What do I put in? I mean, I said it here, right? You specify. Yeah, actually, that's a great answer, right? The answer here is data, but it's not really data. It's actually an address. Most of the time, this is specified by a label. Today, we'll explore a little bit more into that. What is a label and how do you actually jump around, right? But destination here is an address. Again, remember your program is in the memory. So your code is an address. That's how and why you can use a function pointer, right? So the jump basically jump somewhere in the address, in the range that the program's supposed to be. This has a similarity to the go-to command in C, right? This can be interpreted as a jump instruction, and this can be used to implement things like a loop or an if-else, right? On if-else. And on Tuesday, we kind of wrap it up with this conditional instruction where instead of jumping, you would perform a conditional move, right? So that you can eliminate the if else over here. Conditional move eliminate if else by translating that into a straight line code without any jump, right? You would run this conditional move instruction only if, right? Only if something becomes true. In this case, the condition check is less than or equal to, right? And we kind of wrap it up. And today, I mentioned that today we'll transition into how do I implement the loop. And to do this, right, to do this, I will start with a C code over here. I will start with the C code over here. Today, you might have to follow what I'm drawing a little bit more because there's a lot of code and a lot of things going on. All right. Feel free to stop me and ask questions because it can be confusing at times. So what does the C code do? The example we're going to use throughout the first half of today is a program called population count. Population count in this scenario is I take one input called x, right? X is a long integer. It can be any number. The program would perform population count. So let's say if x is gonna equal to this, can someone look at the code and tell me what do I return? Can someone look at the code and tell me what is the result here? What do I return as a result? So in this case, if x is 110110001, what should be returned as a result? I mean, I have the explanation in Word what the function is doing in at the bottom. So someone tell me what's the return value? So what's the return value? it should be a long integer. It is count the number of ones, right? How many ones are in my number in this binary format of x? Let's say x is 110110001 in binary. The program would first AND the last bit. Then you shift the x, right? You AND the last bit, get that result, shift x into 110110000, and the last bit in this case 0. So if you don't do anything, shift to the right again, right? It eventually what it does, it count the number of ones. In this case, there are 1, 2, 3, 4, 5. There are 5 bits that are ones. So the population count in the result here should return 5. The population count should return 5 because every iteration of my loop, I'm gonna go through the loop and the last bit, then I shift the number to the right. I will basically AND the last bit and count how many times my last bit becomes 1. I will keep shifting until x becomes what? When do I stop the loop? I will keep shifting x until x has what value? It's empty, right? Well, empty in the sense, if it's a number, empty means what value? 0, right? Until x becomes 0. Whatever, thank you. So this is an implementation on with C, right? There's a command in C which I actually do discourage you from using because it can introduce random side effects if you're not being careful with this. But there's a go-to command. Go-to would literally move to the label. In this case, you have a label called a loop. Go-to loop means that I'm gonna go back to that place in a loop, right? Why do I implement this code using goto? Why do I implement this code using goto? The reason behind that is the goto version kind of resembles the assembly code, right? I don't have loop in assembly, but I have the jump instruction. The jump instruction it has similarity with the goto instruction. Go there, right? So let's break this down and convert this to assembly by first assuming that RDI is X and RAX is where we store the results. RAX is where we store the results, right? So the first thing we do in the code here is results is going to be equal to 0, right? I'm going to put result as 0. That's how you move 0 into EAX. That's how you move 0 into EAX. Then I'll start doing this. I would AND X with 1, shift X by 1, check if X is 0 or not. If it's not 0 yet, go do the loop. All right, with me so far on the C code. Now let's go to the assembly line by line. I would put in the label called L2. L2 is the beginning of my loop. I would move RDI to RDX. What is RDI right now? What is RDI right now? It's X, right? Now RDI is X. RDX is gonna equal to X again because it's move instruction. Then what I do is I AND RDX with 1, right? In this case, I take this and then, right, and with the value 1, store this into T, which is EDX. So over here, right, EDX can have the value 1 if the last bit of X is 1, or 0 if the last bit of X is 0. Then I'm going to add RDX with RAX. Right now, RAX is 0. Basically, what I do here is, based on the result right here, if the last bit is 1, I'm going to add 1 to my result, right? I'm going to add 1 to my result if the last bit of X is 1. Otherwise, I add 0, which means result equal result. We do nothing. Then we shift RDI. What is RDI? Again, what's the RDI? RDI is X, right? So we shift X by 1. We shift X by 1 and we repeat it again. We loop back, jump if not equal to L2. We loop back to L2. What would be the condition that would get me out of this loop? Can someone tell me what would be the condition that would get me out of this loop? What? How many times do I do this until I have to? When can I stop? When X becomes 0, right? There's no ones left. Did you notice there's no compare here? I did not do compare. I mean, one thing I can do is to compare X and 0, right? But why is it okay if I just do jump not equal and then I'm good? The reason behind that is jump not equal, right? The jump not equal, what does it actually check? Remember from the lecture on Tuesday, jump not equal would check the condition bit. Remember that carry, 0, negative, and sign. I mean, negative is already there. Sign and overflow. Carry 0, sign, which is positive or negative, or an overflow. In this case, what bit should become 1 when I exit the loop? What bit should become 1? The 0 bit is going to have to be 1, then jump not equal would stop jumping, right? And as I said, normal instruction like shift to the right, it will set the bit. So in this case, when I shift X to the right enough that X becomes 0, the 0 flag would be 1. The 0 flag would be 1. What it means is it just tells the processor that, hey, the last operation results in the number 0. Then the jump not equal comes in and check if the 0 flag is set or not. By set, I mean it's 1. Unset is 0. In this case, the 0 flag is 1, which means the last instruction results in a 0. So I'm going to stop jumping. All right. Any questions on the slides? The last instruction, once you're done, you're returning. To be honest, I actually don't know why the compiler put repeat here. REP is a repeat instruction, so you're gonna repeat the return. In this case, I don't think there's a need to repeat this. You can just return. So I'm not sure why the repeat is there. But, okay, yeah, sure. So the question is, can I say the loop part again? So at least, is it clear that the loop start from here, right? The loop start from here down to here. This is my loop. L-O-O-P. So is that clear for now? Like that's the loop. Yes. Okay, awesome. So what does the loop do? The first thing I do is I want to do X and 1, right? This is the first thing I want to do. X and 1. Right? To do that, the assembly over here use EDX. It used EDX as a temp variable. So I use EDX as a temp. T is temp variable. And I take X, I AND 1 with X. And then I would add RDX. RDX is a 64-bit version of EDX. I would add RDX to RAX. In this case, I'm basically doing this. Results equal result plus equal T. Results is gonna equal to T plus the old version of results. And then you shift RDI. RDI is the variable X. You shift RDI to the right by 1 bit. You shift RDI to the right by 1 bit. All right. Is it more clear? So if I want to link it back to the C code, right? These two instruction is this line. This instruction is the add right here. This shift is the shift right here. And the jump is this basically check and then go to. All right. So if you want to pair it back to the C code that we have seen on the green box here, move kill and the and instruction is basically doing x and 1. X and 1. $sign means the number 1. When will jump not equal to stop? Awesome question. Jump not equal would basically keep checking this bit in the condition code, like conditional register. So these are special register that gets set every time you have an instruction. The C bit, the 0 bit would get set when the last instruction results in the 0. So when does the shift, right? The last instruction is shift. When will the shift instruction result in a 0? Can someone tell me when the shift instruction would result in a 0? I keep shifting X, right? When will that stop? When will the shift result in a 0? Let's say I have this number 10111, right? When there's only ones left, yes. So the first shift would get rid of this. The second shift would get rid of this. The third shift would get rid of this. The fourth shift would get rid of this. It's not 0 so far. The last shift would get rid of this. Your number now becomes 0. When that happened, the 0 flag would change from 0 to 1. That's when the C bit would get set from 0 to 1. Jump not equal would look at the flag here and check, is that 0 or is it 1? Whenever that's a 1, which means basically whenever there's a 1, it means the last instruction results in the value 0, right? That's when X gets shifted until it turns into the number 0. You stop jumping because it's jump not equal. It's jump not equal. If it's not equal to 0, you keep looping. If it's not equal to 0, you stop looping. All right. Is it more clear now? Okay, awesome. Any other questions? Because that's basically it for the implementation of the do while loop, right? And we can use this concept to generalize whenever, right? Whenever we see a do while loop, we can do it this way. We first convert to the go-to version. You have the loop body, then you have the condition check, like first step, second step, and then you go back to the loop again, third step here, right? Clean, easy. The loop body can be whatever code you want to put in, right? It's clean and it's easy. So we are done with do while. All right. What are the other type of loops that you can have in the world? Can someone tell me what are the different format of looping? Except for the do while. What else can I do? You can use a for loop and you can use a while loop, right? So let's do a while loop first because it is closely resemble do while. So what are the difference between a do while loop and a while loop? So the while loop can be written this way. Right? So what is that one difference? It is really similar to the do while, but what's the difference here? You check before running, right? You check the first thing you do. First step, you check. Second step, then you will loop. So, you can translate this into the format we call jump to the middle, right? When you compile the the while loop has this jump to the middle format. What's the first thing we do in the while loop? We check, right? We check. So the first thing we do is we check, we go to test, and inside here, there is going to be a place in the code that tests if things are true, right? So this is basically the first step. Then if it's true, then you loop the second step, right? The second step. And then you come back and test again. The reason why this is called jump to the middle is, if you notice, right, the test part is here and here, right? And here. So this is where you test the code if it's true or not, and you would loop around. The loop itself is here. This is the loop part. You see how there's an overlap between the test part and the loop part. That's why we call it jump to the middle. You first test, the test kind of encapsulate the loop. The loop would kind of jump to the middle of the code block here, right? So can I translate the code that do population count? This is the while loop, right? The while loop would first check if x is 0, do the and do the shift. Again, same code, using while loop instead of do while, right? With me so far about the C code to the left. Anyone not clear about the code to the left? All right, if you're not clear about the code to the left, please type in the question. Now I'm gonna start going through the code to the right. The code to the right, the only difference is now we implement using goto. Again, we check the condition first, so you go to test, which is here, right? If test is true, then we loop it back here, right? So this is the first step, second step, third step, then you loop it here, fourth step, and repeat, and repeat. Comparing to the code we've seen earlier, basically, initially we start the loop at test. You start the loop at test. You first test the code and you loop and you test again, you loop, you test it again. The small problem with this, right? The small problem with this is, as I said, there's quite a bit of an overlap between the loop part and the test part. Because if I want to draw where is my loop, my loop is here. This is, oh, sorry, I somehow circled return. I should not do that. So this is my loop, right? But if I want to draw where's the part that I test, the test goes from here and has this part here as well. So this is basically the test part. In compiler sense, right? If you want to optimize the code, if the compiler want to automatically, exactly, yes, thank you so much. This look like a really not that effective while loop in terms of optimization, because you have this overlapping between the two blocks of code, right? One thing you can do to make it more efficient is you would change, right? You would change the while version into do while. That's the first step you can do. In GCC, you can use -O1. -O1, O means optimization. O1 is turning the first level of optimization. In GCC, you can use -O followed by a number here. So you can do -O3. O3 is kind of like, I'm going to enable every optimization GCC knows, and they kind of test it already that it's safe and should be correct. Your code would magically be faster. In many cases, actually, it's not magic, it's science, right? But it's been proven that these techniques can make your code run faster through optimization. So you can do -O1. O1 would perform this optimization, changing while loop to do while. Why and how do we do this? How do we do this? The difference between the while loop and do while is we first test the condition, right? So if we want to use a do while loop, we need to check if the condition is wrong. If the condition is wrong, we are done, right? In the while loop, if this is not true, we don't have to loop. Again, if the test is not true, we stop the loop. So we test if test is not true, we are done. We first check if test is not true, we're just done. We skip to the last line. Otherwise, we are now back to do while. Do while. So you can use this implementation using goto, right? If not test, you go to done. Otherwise, you separate out the loop body, which is this. This loop body, let me call this code block A. Code block A is now totally inside, right? Totally inside. There's no overlap. The test is just inside this loop. There can be a lot of optimization in compiler that can make this loop faster using different tricks, right? You can enable further optimization on GCC to hopefully this becomes faster. All right. Any questions so far? Any questions so far? The reason why compilers change from a while loop to a do while loop is, well, it's been shown that this is faster. And that's all. It's been shown that this can potentially be faster. All right. Any question? Okay, so if there's no question, right, over here, right, this is the conversion from our population count into from the while to a do while version. If not X, if like instead of while X, I first do if not X, we're done. Go to the end. Otherwise, we have this inner loop that would check, right? I loop around, the loop body is to and the number shift, and then if X, go back to the loop. So again, as you can see here, this code block A is encapsulated and is independent from the first condition. You can do whatever inside this code in terms of optimization. All right, so we are done with the while loop. We are done with the do while loop. What's left? We have the for loop, right? We have the for loop. This is probably one of the most common way to write a loop, right? What does the for loop entail? You have the initial condition, we have the test, and we have the update, and you have the loop body at the end. The way this is run is first you would do initial condition, then you check, then you do the loop body, and then you update. Right? So you can implement the population count using a for loop this way. For I equals 0, I is less than the size of the long integer, right? In this case, the size of the long integer. And then I plus plus. And then I'm gonna basically do the same thing. I'm gonna go from X shifted by I, right? And 1, right? And then I'm gonna add the bits. So in this case, the initial condition is what? I'm gonna start with I equals 0. I'm gonna test if I is less than W size, which is defined right here. And then I'm gonna increment I. And here's the loop body, right? The loop body is again shift and add, right? What typically would happen is this for loop would be converted to a while loop, something like this. Initial condition, while test, do the loop body and update. Initial condition, test, run the loop body, then update, and then do it on repeat, right? So now we have the initial condition, test, update, and body. You can use the while loop to implement the for. Initial condition at the end, then use the while loop. Then this is the loop body. And here is where you update, right? And as I say, the while loop is not that great. So I want to then convert to a do while. Then I can convert to a do while. So over here is the conversion. That's the for loop, right? Great question. So is everything in the end turns into a do while loop? Yes and no. Depending on what techniques in terms of compilation techniques that you want to apply, right? Because to be honest, who knows, right? In the future, someone might come up with a really great technique that combine the programming language and compiler together that have a different version of a loop. That would be fast. But for now, it kind of makes sense to convert the for loop into something like a do while. But the for loop is nice, right? From the programmer point of view, it gives me a lot of power to initialize and update. So do you have to worry about this? So let me ask you about this. If you write a for loop, do you ever have to worry about performance in terms of, oh, should I just convert this to a do while? Do I have to worry about this? You don't think so, and you are correct, right? This is one of the tasks for the compiler, right? In terms of thought, right? The thought process, the for loop is kind of nice, it's compact, right? It's kind of compact, it's nice, and it's actually work well, right? So we can use for loop. The job, the actual component that should be worried about this is the compiler. This is this is why, actually, to be honest, let me put it this way, right? You put the right person for the job. This is basically what everyone should be doing, right? You should put the right people to each job. It should not be based on network. It should not be based on whether that person is rich or not. It should not be based on whether that person knows someone higher up or not. You should put the right people to each job in the ideal world, right? In reality, I'm not going to talk about it. I want to forget about reality. But in the ideal world, you should put the right people for each job. Over here, you are writing the program. Your job as a programmer, make sure it's well written. The best component, the best part of the computer that should be worried about this should be the compiler. GCC should be worried about this. Do you notice that GCC has version as well? Anyone try to check the version of your GCC? Otherwise, I'm going to show it here. So one thing you can try is you can type in, can you see the screen? It's actually quite small. Let me change the font. So can you see the screen? Hmm. Okay. One thing you can do is to check the version of GCC, right, by using dash dash version. And you might have noticed that GCC has the different version. This means that GCC also evolved over time, right? This is one of the big area in computer science. How do you build a compiler? Right? How do you build a compiler? The compiler people would work with both the hardware people, OS people, like system people, PL, programming language people, and the programmer. so that you can get the compiler to do fancy tricks as I mentioned, right? It would do this conversion for you. You don't have to worry about this because at the end of the day, it would perform the conversion and it should, in theory, behave the same way. All right. Again, put the right people on a job. Now it's the task of the compiler. If you are curious, and I'm going to talk about it toward the end of today's class, right? If you are curious and you want to work in compiler area, where should you, like basically how should you design your the things you should learn in order to know more and in order to be able to optimize your code uh, automatically for every single programmer, right? This is basically, if I build a new compiler, it works for all the programmers who use my compiler, right? So everyone would enjoy this benefit. Again, I convert the for loop version into a do while, right? A do while loop. How do I do this? Again, there's an initial condition. Instead of checking for test, I check for not of this. If it's true, you go to done. So that I finish the first check quickly, I go to done. Then you have the loop body followed by update, followed by test again, right? So this is basically your loop. This is basically your loop. And now you have the do while loop. You can even optimize, right? You can even optimize the initial test because you know that I is going to be 0. So by default, if I is going to be 0, what can I tell about this condition check? What can I tell about this class? If I is 0, do I ever jump to that? Yeah, it's always gonna return false. So you go into the loop, right? So you can even eliminate this. This is another trick that compiler can do. The name of this trick is called constant propagation. Constant propagation means that if I have a variable and somehow it turns out I know the value of the variable, I would put the value in. I is what in this case? What's the value of I? 0. I'm gonna replace I with 0. What's the value for W size? If you look at the earlier slide, you know W size is greater than 0. Can I evaluate this? I don't even have to run it, right? I know the result of this. It's gonna be false, right? It's gonna be false all the time, so I can get rid of this. Compiler also detect this and get rid of it for you, right? So this is the beauty of having a good compiler. They would try to detect all these things and get rid of unnecessary code for you. It can even reorganize your code to do fancy things to make it faster, to make your program faster. Anyway, let's come back to the content of this class. How do we use loop, right? So now, right? Oh, you mean can the compiler show the unnecessary code? So have you seen something like this? Warning, unreachable code. Oh, not yet. Okay. So let's say I have something like this. If 1, if 0, for example, if 0, and I have some code here. Else, something here. What can I tell about my code? Well, it never run this part, right? It will never run this part. Compiler actually will detect this and will give you, for example, warning that you can't reach the code here, right? This can happen. I got it quite a lot actually. When I built a program that gets bigger and bigger, what can happen is I add more code in and I forgot to delete something out, and it gives me a warning, hey, unreachable code, or These variable, and another common warning that you can get as a program get bigger is something like this. Something like unused variable. Sometimes you have declare a variable, you assign a value to it, but you never use it later. You never use it later. Compiler also have a technique that can detect these things, right? It detects what we call is like liveness. Do I actually use the variable, or is it not getting used? So there are actually quite a lot of analysis that has been developed into theory inside computer science that go into, hey, can I detect code that are suboptimal, code that never run, code that can be replaced by something faster, and how do we systematically do this? Because compiler is automatic, right? You compile the code, and I could agree to that, right? My brain doesn't work that way. I cannot understand every single thing that compiler people are trying to do. I find these folks to be really smart. But it's a program. GCC is a program. You actually write a program to compile another program, right? That's what the compiler is for, and that's actually a big group of people in the world, right, that work on compiler. Google, for example, would hire people who do compiler to optimize the code in Google. Facebook would do the same thing. Microsoft would do the same thing. I can assure you that every single large tech company need people who do compiler to optimize their code. Um, and sometimes you also come up with a new language too. You see common things that certain language are not expressive enough. You cannot do certain things, so you change the language or you extend the language so that it can do fancy tricks. So these are actually advanced, yeah, like C++, right? People realize that, hey, C is great, but it has limitation that I cannot have the concept of an object. But this is less compiler and more of the programming language. It's a property of the program. It's a property of the language. Actually, it's a property of the language. You come up with a new language that are more expressive, that can represent object, right? So that's why sometimes people come up with different language because they want to be able to express more things or to want to be able to make it easier to program, right? For those of you who hate C and it's hard to program, that's exactly why people come up with Python and Java, right? So hopefully this is also another motivation. It also, I hope this kind of trigger your curiosity about the, I guess, the science behind building your computer, right? Not just building the software, but build this whole thing end to end. There's a lot of science that go into that. Anyway, so I go super sidetracked, right? The next thing that we need to understand is now we know how to use for loop, while loop, do while loop, if else. If else is easy, it's just based on the condition you jump. The next thing that we haven't talked about is switch case. And before we dig deeper into this, because it's another big topic today, let me take a 10 minutes break. Let me do a 10 minutes break. But while we are taking a break, please take some time, like 1 or 2 minutes, to look at the code to the left. And because we work with this code, right, from now to the end of this lecture, we are gonna work through this code. The code takes 3 inputs, X and Y and Z. It return W. W is the return value. Whatever you do would be based on X. X would be checked. The value of X would be checked to do certain things with the value Y and Z. All right. So we'll take a break. We'll meet again at 3:05. We do 10 minutes break. In the meantime, go get coffee, go get some tea, making sure you are freshened up, and we'll come back at 3:05, resume the lecture. All right. I'm gonna pause the video for a bit so that when you watch the video, there's no break. And as I said before the break, right? We're gonna look into the switch case and see how this would translate into assembly. And one of the common things that actually get used in assembly is called a jump table. We will learn about this technique by using the switch case as a way to motivate how and why the jump table can be useful. All right. So over here, the switch case statement has a few things, right? There's a missing case. For example, in here, you can see that when x is 4, you go to what? When x is 4, what do? You go do the default, right? Follow through is when x is 2, right? You would run this, follow through 3, run this as well. So it would do W equals Y divided by C, followed by W is going to equal to W plus C. Then there's a share label like 5 and 6, right? 5 and 6 over here. Both of them would actually, sorry, too big of a circle. In this case, W would do W minus C. All right, so these are basically the program that we're gonna look into and how this get translated to assembly. Again, similar to a loop, there's a setup part, right? So there's a setup part for the switch case, right? So what are the setup parts? Over here, you initialize W to be 1, followed by the switch and followed by return, right? Let's assume that X is in RDI, Y is in RSI, and C is in RDX, and we return the value to RAX, right? And quick note is that W is not initialized anywhere here. We have this initialization here. But in the setup code, we don't have this initialization. This would be explained when we have the full-blown code for our switch case in this part. But let's look at the setup part, right? The first thing we do is to move RDX to RCX. What is RDX? What is RDX? It's C, right? So basically over here, I said percent %RCX is going to equal to C. The only reason why it's here is if you look at the full code, RCX is used for the division where we do Y over C. I think that's the only instance of when RCX gets used. That's when you want to compute Y over C, which is one of the switch case statement. What does the compare do? I want to compare 6 and what? I want to compare 6 and what? And X, right? I want to compare 6 and X. If X is greater than 6, jump above, right? Jump above. If X is greater than 6, we jump to L8. Let's assume L8 is somewhere. Anyone want to take a guess? What is the code in L8 do? What would happen if X is greater than 6 based on our switch case statement? Sorry. Yeah. So if X is greater than 6, what do we do? You go to the default, right? You go to the default case. So in here, anyone want to take a guess what should be the code at the label L8? If you jump there, what should you find? So L8 should contain the default case, right? You assign, exactly, yes, assign to W. Thank you. That's a perfect answer. And then we have this weird jump call, right? Over here, jump always, but what is this? You have star dot L4 followed by parentheses percent RDI 8. What the heck is this? So let's break this down. This technique is called indirect jump. This technique is called indirect jump. I'm gonna go to the next slide and I'll make sure I copy this part, right? That part is again percent dot L4 in parentheses, comma, percent RDI 8. All right. So in assembly, when you have parentheses, what does it mean? Whenever I have parentheses in assembly, what does it mean? It's an address. Yes, it's a location. It's an address. So remember our addressing format from lecture on Tuesday. You have D, base, index, and the scale, where we said this address equal D plus base plus index multiplied by the scale. Remember this from Tuesday. So this is how we can specify the address. So if you compare this formatting with this thing, can someone tell me what's D? What's D? L4, yes, thank you. So D is L4. What's the base? What's the base? This is a little bit of a trick question. So what's base here? Do we have the base? We don't have the base, so we get rid of this. 0, right? If there's no base, if you don't specify the base, you don't need it. 0. What is our index? Yes, actually, thank you. Index is RDI. RDI is X. Scale is 8. So the address, right? The address is of this is going to equal to L4 plus X multiplied by 8. Because RDI is X, 8 is the number that we multiply to RDI. So that's our address. Let me give you one example. Somehow, let's say .L4 is at 0x1000, and then X is 3. What is this address that we are trying to jump to? What is the address that we are trying to jump to? The address would be, right, 0x1000 plus decimal 24. So be careful with decimal numbers. 24 is 16 plus 8. So this is basically going to be 0x1000. I think, what is 4? 4 is, yeah. So this is the address we're jumping to. 14 is 24. 14 in hexadecimal number is, I'm wrong. 14 is 20. Yes, thank you so much for the correction. Yes, it should be 1018. 18 in hexadecimal number is 24. The reason behind that is 24 is 16 plus 8. It's 16 plus 8. So 16 plus 8. 16 is 10 in hexadecimal. 8 is 8 in hexadecimal. So you add those two together, you get 1018. All right, so that's the address we jump to. In the jump table, you would see something similar to the table I have to the right over here. So let me highlight it. So this is our jump table. Let's break this down line by line, right? Let's break it down line by line. And yes, the RDI over here is our X, right? If you look at the code earlier, you might go back one slide. If we go back one slide, you will see that RDI is X. So over here, RDI is X. Now, if you look at the jump table, what do you have? The first line, say section.ro data. RO data is read only. Basically, it's specified to the computer saying that, hey, these are data that you are not supposed to modify. It's read only. Put that in the region that only can be read but not written over. So that's what the purpose of the first line do. Read only data. The second line, align 8, it means that whatever go next, I want them to be aligned in 8-byte granularity. Each line is 8 bytes. Over here is 8 bytes, 8 bytes, 8 bytes. Every single line here are all 8 bytes. Every single line here are all 8 bytes. Then what you put in here would be the 8-byte address. And it turns out that .L8 would be some address that point to the line that L8 is pointing to, right? .L8 would point to the line that basically the code label L8 is pointing to. It can be any address in your program. It can be any address in your program as long as it's 8 bytes long. These are indirect jump because our jump instruction would first check here. It will first check here. Then you will know, right? You will know, do we go to this address or this address or this address based on what? Based on what? We start at L4. How do we move from L4, from the first line to the second line to the third line to the fourth line? What make our address change? What is X? What is X? It's RDI, right? So let me give you one example. Let me do it maybe here. Let me erase it first, right? If X is 1, can someone tell me what would be the address here? If X is 1, what do I get? I do get L4 plus what? Plus 8, right? So L4 plus 8. L4 is right here. This is L4 plus 0. This is L4 plus 8. This is L4 plus 16. This is L4 plus 24. This is L4 plus 32. This is L4 plus 40. And this is L4 plus 48. So if I have L4 plus 8, which label do I jump to from this table? Do I jump to L8? Do I jump to L3? Yes, we are then jumping to L3 because if you look at L4 plus 8, you see L3. What if I have X to be 5? What do I jump to? If X is 5. L7. All right, awesome. So actually, this is a common technique in assembly programming. We use this quite a lot. When you have multiple function calls that have different parts everywhere in the code, you can use the jump table. You can use a jump table to perform indirect jump, and the indirect jump would be in this format, in the format right here. All right. So for now, you know, right, how to get where to jump based on the value of x. If I give you the table, if I give you the table that looks like this, you know where are we jumping based on the value of x. All right. Now let's kind of generalize this. Let's generalize this. Let's say we do switch x, and then case x is 0, x is 1, x is an n minus 1. Each case has this code block, right? The jump table format would be divided into something like this. This is when x is going to be 0, x is going to be 1, x is going to be 2, blah, 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 x equal n minus 1. The table itself would contain the target address for each of this block, right? It would point exactly at the first line of these blocks. It will point at exactly the first line of these blocks. So if we go back to our example, the switch case in C over here, right? You can see the link between each case, right? Our table, if x is 1, you jump to L3. So you know that this is where L3 is located. This is the code that performs W equal Y multiplied by C. If x is 3, right? If x is 3, it's jump to L9. So you know that this code is where L9 is located. It would go and do W equals W plus C, right? And you can have the share case like here. If x is 5 or 6, it both go to L7, which is this line, where it would do W equals W minus C, right? So that's how you can specify the jump table. You can actually write this in assembly. Most of the time, the compiler would generate this for you. It would detect the switch case and it would populate the table for you. All right. Again, the beauty from the compiler, they all do this for you. Somehow it changed to assembly and it would run, right? So now let's dive into what happened. Now that we have indirect jump right here, right? We have indirect jump right here. I will start to show you a big assembly code that represent basically the assembly code that I am going to show next would represent the code here, the code that do the switch case. All right, so it would be quite big. It would be quite big, which is this. We will do one step at a time. Again, remember, actually, I forgot already. X is RDI. Y is RSI. C is RDX. Right? What does the first line do again? RCX is going to equal to C. This is going to compare 6 and X. If X is greater than 6, where do we jump to? Because we do jump above, where do we jump to here? If X is greater than 6, where do we jump to? The default case. So what line here? If you look at the assembly code, what line? At what address? What address? Do you see 400,614 anywhere in this, in the code here? So if X is greater than 6, it would jump to line at address 400,614, which is right here, right? This is when X is greater than 6. All right. What does it do? It's default. So what does default do? W is going to equal to 2, right? And we put that into EAX. In this case, it's in EAX. So it's already returning W, which is right now 2. And you return, right? Return RETQ is return from the function call. All right, clear. Are we all clear on the default case? The next thing we have is we now have the indirect jump. Yay, fun. Indirect jump. So what is L4, right? We used to have L4. In this case, what's the address of my table? What's the address of my table? Where's that table? How can I find it? $4007F0. Correct. Yes. So over here, if you can somehow print the content of $4007F0, you will get this. You will get this thing. Starting from 4007F0, the first information is the first 8 bytes. This is the first 8 bytes is when X is going to equal 0. The next 8 bytes is when X is going to equal to 1. Again, the next 8 bytes is 400800. This is going to be X equal to, X is going to equal to 3, X is going to equal to 4, X equal to 5, X equal to 6. And then this is when X is going to equal to 7. Do we ever reach here? You see that the number here is weird, right? It's just some junk value. Why is it okay? Why is this okay? Yes, actually, yes. Because we already checked, right? If X is greater than 6, it's go to default, so we never would be reaching this part. We will never reach this line. All right. So let's go to when X is going to equal 0. Where does it jump to? If X is 0, where do we jump to? Yep, the default, oops, sorry, wrong slide. The default, right, so when X is going to equal to 0, you go there as well, 400614. When X is 1, we jump to here, 5F0. So again, sorry. When you have X, which is 1, this is this line, when X is going to equal to 1, what do? We move RSI, which is Y, right? So RAX is going to equal to Y. Then you multiply RDX. RDX is C, so RAX is going to equal to Y multiplied by C, and you return. So that's when X is going to equal 1. When X is 2, you jump to 5F8. 5F8 is right here, right? This is when X equals 2. What you do here is you move RSI, that's Y, right? So now RAX is going to equal to Y. Then this combination over here, would divide, right? RCX is C. This would divide and put and calculate Y divided by C. It would calculate Y divided by C. Then, if X is 3, you go to 602. 602 is right here, right? 602 is right here when X is going to equal to 3. And remember, our X equal to would keep running. It would then jump to 607. 607 is when the continuation, like the continue of x equal 2, because you do divide and then you jump to 607. 607 is doing what? Exactly, yes. So there's a comment on the chat that this is a lot more efficient than checking using compare at every case. You're correct. This is much more efficient. So when x equal 2, you jump to 607. What you do here is you do w is going to equal to, I think, w plus y over c for x equal to. But if x is 3, then you first do this. W equals 1, and then over here, W equals W plus C, because RCX back here is C. So now we covered the case where X is going to be 2 and X is 3. Return, right? We are almost done. When X is 4, you go to 614. 614 again is default. So when X is equal to 4, you do the default case. When x is 5, you do 6OB. 6OB is right here, right? This is when x equals 5. What do? We first do w equals 1 and you subtract. W is going to equal to w minus RGX is C. Then when x is 6, you go to 6OB. 6OB is right here again, right? So this is when x is 5 or 6. We do the same thing and we return. And now we are done. Now we are done. All right. Feel free to go through this table again. Feel free to go through this table again. But now we are done. We have covered from x is equal to 0, which is the default case, to when x is 6. The next set of slides is the same thing, but I have broken it down to each case. For example, when x is 1, we do this part where you would first put y, like w equal y, and then over here, w equals y multiplied by c. When x is 2, then it has a fall through, right? So you would first do this, then fall through. First do this, then go here. If x is 3, you first do this, then go here. It fall through, so that's why it's doing this. And when x is 5 or 6, it's a share case, so you will see that it jumped to the same level, L7, right? And as does the compiler do the same thing with else if? Yes and no. Yes and no. That's a great question. Yes and no. It need to detect, right? It need to first detect what you're trying to do. It will first try to detect what you're trying to do. And for example, if you have something like this, case 1 and then case 1000, you only have 2 cases. What will happen if we use jump table? How big is that table? Let's say each entry is 8 bytes. How big is your table if you have to cover from 1 to 1000? Because you have to do the jump table for, it's going to be 8,000 bytes, right? So in this case, if the statements are sparse means that you only use a few cases, the rest go to default. You would convert this to if else. Does the compiler do this for you? Yes. Again, put the right people for the job. Over here, it's totally okay to leave it to the compiler. It's totally okay to leave it to the compiler because they have the perfect information from your program and they can do this conversion for you. All right. And now that conclude the lecture part today. But before we leave today, I want to bring up a few things, right? I know that this is the introductory class to computer system, right? That's why it's called system skill. This is the first class ever that you have to deal with these things. In the future, if you somehow get mad like myself and keep pursuing the system track, right? Pursuing the system track like I did with computer architecture, but I enjoy more building or more the building the hardware, right? I still don't have the brain to do the compiler, but I like building the hardware. You want to be mindful that the assembly you compile, for example, can be different based on the ISA from x86 to ARM to MIPS, which is what you have in PlayStation 1 and PlayStation 2, or even things like IBM Power. This is the supercomputer by IBM. They use a Power ISA and Power architecture. It depends on the compiler as well as the compiler optimization. One thing that I encourage you to try is when you have GCC, try to add -03. As I said earlier, -03 would try to enable most of the compilation techniques that GCC know, and they have tested already that it works. Unless you have some special edge cases, it should work. And you can notice the performance improvement if you have a big program. If your program is big, you might see speed up. Your program might magically run faster. All right. If though for those of you who like doing these things, I would also encourage you to, or at least if you're curious about it, right? There's a framework. It's an infrastructure project. It's a huge project done by a group of awesome researchers across the world, like everywhere. It's called the MLVM compiler project. I'm showing you the screen here. That's the website. Anyone here use a Mac? Anyone here use MacBook? So for those of you who use MacBook and you want to compile C code on your MacBook, what's the command that you need to do that? Do you use GCC or not? Anyone try doing that before? So in Mac OS, they would rely on CLang. CLang is the GCC. It's like an equivalent of GCC. But one thing the Apple laptop and the Unix-based system in Mac OS did was they implement their own compiler for C. So you would use CLang to compile because it's based on this LLVM project. Many of the research in compiler is built on top of this project. The one that turns into the actual product sometimes gets integrated to the GCC that we have. It gets integrated to the GCC that we all use so that we can enjoy the benefit of that, right? So if you somehow want to pursue this track, right? I want to do compiler research. I want to do compiler engineering. I want to make sure that my code is fast. You can check it out. It's a little bit advanced based on where you are. I just want to bring it up so that if you're curious about it, feel free to check with me or Ajahn Kanat or Ajahn Sansern. We all know about this project. It's really, really nice, especially if you say, hey, I want to try something crazy for your senior project. Another thing is, if you want to build your own ISA, right? There's also another open ISA. It's not x86. It's called RISC-V. This is open and free. This is a project pushed by the academia side of things, where people in academia, they realize that, hey, there's not a lot of ISA that you can get for free, right? If you want to run a startup company that builds certain piece of hardware, you need to be able to program the hardware. To make it easy to program, you would need an ISA, the language for the hardware, that can be used across different devices. So they come up with RISC-V. This is the website for the RISC-V project. If you go there, you can see some sample actual products that are built based on RISC-V. I would say RISC-V is like the spiritual successor for the MIPS processor. It's a spiritual successor for the MIPS processor, the one that goes into PlayStation 1 and PlayStation 2. These are the open things in this area of computer science that most people in Thailand, to be honest, didn't even realize exist, right? There's quite a lot of area in computer science that go into how to build your computer, how to build the system, how to build the compiler, how to manage the storage, hard drive, and SSD that you plug in. It's it worked like magic, right? In reality, these are all science. Science is make sure things work like magic without any problem. Well, most of the time we have bugs, but hopefully most of the usage won't run into those bugs. If you're curious, feel free to let me know. I would be more than happy to share more information. All right. Now, with the last minute question, we don't have in class exercise for this week, right? Yay. What I want you to do is we are going to go to Discord because assignment 3 is now up. Check it out. Read the PDF. If that, don't cry. Come on, guys. Assignment 3 is up because assignment 2 is already due, right? We need to keep up with all the crazy work we're giving you guys. If you have any clarification questions, let me know. You have 2 weeks to work on it. As I mentioned to the student in section 1, I like this assignment a lot. I think it's fun. A lot of people also find it fun. A lot of people find it not so fun as usual. But now we're gonna switch to Discord for the last, I would say like 15 minutes, the remainder of the time we have. I'm gonna wrap up the lecture part and stop the recording.